Welcome back, everyone. Ready to dive into something pretty out there. We're tackling quantum gravitational redshift today, or QGR for short. After that mention of Mr. McSherry's work on it, well, we just had to dig deeper.
Talk about a cosmic head-scratcher. It really makes you rethink redshift. We're so used to picturing galaxies racing away, but QGR, it's saying maybe it's the light itself getting tuckered out on the way here.
Tired light, huh?
Mm-hmm.
Okay, before we get ahead of ourselves, we've got this paper, get this, it's called Quantum Gravitational Redshift, straightforward enough, and it lays out this idea that maybe, just maybe, redshift, that stretching of light towards the red end of the spectrum, it might not just be the universe expanding, right? What if it's photons, those little light particles, actually losing a bit of pep in their step thanks to, wait for it, gravity itself?
Gravity playing bumper cars with light, basically. Imagine the universe is this massive obstacle course, and these photons, they're bouncing off countless little gravitational speed bumps as they travel. Every bump, tiny energy loss, shifts the light a smidge toward the red.
And over, what, billions of years, trillions and trillions of miles, those little nudges, they build up into the redshift we see from these mind-bogglingly distant galaxies. So instead of the universe puffing itself up like a balloon, we've got light kind of losing steam.
You got it. And here's the real kicker. No need for this dark matter, dark energy, even inflation gets tossed out. This QGR, it's elegantly simple.
Hold on a sec. Dark matter, dark energy.
Yeah.
You make it sound like cosmic ingredients or something. But no, seriously, you're just casually dismissing some pretty major cornerstones of modern cosmology here. Tell me more about this whole elegance thing.
See, the Big Bang model, it's great and all, don't get me wrong, but there are these little hiccups. It needs these unseen things, right? Dark matter, dark energy to explain why galaxies spin like they do, or why the universe seems to be speeding up its expansion, not slowing down.
Yeah, it's like we know something's out there pulling the strings, but we can't actually see the strings themselves.
Yeah.
Like trying to solve a jigsaw puzzle with half the pieces missing.
Exactly. In QGR, it's like, hold my beer. And it tries solving the puzzle with the pieces we do have, suggesting maybe those missing pieces are just us looking at the picture wrong, misunderstanding redshift this whole time.
Okay, starting to see why this QGR thing is so appealing. But how do photons just lose energy to gravity like that? Feels like we're about to tumble down the rabbit hole of quantum physics here.
Buckle up, because it's a doozy. QGR leans on this idea of virtual photons. Think of them like ghost particles, popping in and out of reality in the quantum world. They're like these tiny, ghostly messengers carrying forces.
Ghostly messengers, you're killing me.
I know, wild, right. But bear with me. In QGR, these phantom photons, they're constantly mingling with real photons. Picture our little photon traveler running into, let's say, a massive galaxy's gravitational field, which, according to QGR, is just teeming with these virtual photons.
So our little photon buddy, on its epic voyage, bumps into these ghostly particles, and every interaction, bam, saps a tiny bit of its energy.
Exactly. Now, you might be thinking, is there anything else in physics where energy gets swapped around like this? And there is. It's similar to what we call Raman scattering, where photons and molecules get into it, the photons lose a bit of energy, changing their wavelength.
So we're basically talking cosmic scale Raman scattering, but with gravity playing the role of those molecules, right?
It's okay. But there's a catch. Raman scattering, it's wavelength dependent. Different colors of light, they get affected differently. QGR, though, it's scattering. It's thought to be wavelength independent.
Is that why when we look at those super distant galaxies, all the colors of light have been redshifted the same amount?
You nailed it. That's one of the things that makes QGR so darn compelling. It just naturally explains this wavelength independence, which honestly the standard model kind of struggles with.
But like the universe has this giant filter on it, shifting everything towards the red no matter what.
That's a pretty poetic way to put it. And this brings us to another big point for QGR, the cosmic microwave background, the CMB.
Ah, the CMB, that faint afterglow of the Big Bang.
Right, that's what we're used to thinking, but QGR, it's like, hold on a minute, what if the CMB, what if it's not leftover heat from a single event, but a giant cosmic smoothie of photons, all ages, constantly being redshifted over, well, forever.
So not a fading echo of the Big Bang, but this constant hum of light, always being refreshed by this QGR scattering. It's a pretty wild way to look at it.
Really flips the whole cosmic timeline on its head, yeah. The CMB, it's not a postcard from the beginning of everything anymore. It's like a live feed, always updating, showing us the universe at work.
I like that, live feed. But hold on, if these photons keep losing energy, wouldn't they just like fizzle out? How's QGR explain why we can still see anything from these crazy old, crazy faraway objects?
That's where QGR gets really interesting. So it suggests that as these photons bleed energy, through those interactions, they actually lose it slower over time.
Almost like they're approaching some kind of energy bottom, but never quite hitting it.
That's the idea. Picture a ball bouncing down a staircase, but each bounce, it gets smaller and smaller. It could, theoretically, bounce forever, you see, just tinier and tinier. QGR, it uses this concept to allow for a universe that might be infinitely old, but still full of light, even if that light's been seriously redshifted.
Whoa, that's trippy, but kind of beautiful, right? No beginning, no end. The universe just is.
And that's part of what makes QGR so fascinating, even if it kind of shakes up everything we thought we knew. But gotta remember, it's still theoretical, right? We gotta test it.
Right, we can just take its word for it. How do we even test something like that? What could prove it or disprove it?
Well, one way is binary star systems. Two stars orbiting each other. QGR, it says that light from the farther star, as it passes the closer star's gravity, it should redshift more than general relativity alone would say.
So if astronomers can get a really good look at that background star's light, measure the redshift super accurately, they might see this extra redshift, and that would be a point for QGR.
You got it. And it's not just about proving QGR is happening, it's how much redshift. This could totally change how we understand the universe's expansion.
You're talking about the Hubble tension. That whole debate about how fast the universe is expanding, some measurements saying it's faster, others slower, right?
Exactly. QGR might be able to clear that right up. Think about it. If we've been overestimating distances this whole time because we didn't account for this extra redshift, well, the universe might not be expanding as fast as we thought.
That would be huge. Like finding that one missing puzzle piece, suddenly everything makes sense.
It'd be a revolution in cosmology. But we need more research, of course.
Right.
There are other ways to test QGR too, like looking at supernovae, those massive star explosions.
Right, those are like our cosmic lighthouses, how we figure out how far away things are in the universe.
Exactly. But if QGR is right, those lighthouses, they might be dimmer than we realize. I mean, if those supernovae are farther than we thought because of this extra redshift, well, that changes how bright we think they really are. And that changes the distances we calculate to their galaxies.
Like realizing your ruler's been shrinking. Suddenly, everything's farther away than you thought. It's really making me rethink just how vast everything is out there.